Okay, so I'm gonna jump in here. You see my memes? Okay, I wanted to find something that had to do with molarity, and I didn't really see a lot of good molarity memes. Okay, so I made up my own. So students ask me, "What is this?" And I say it's a 3-molar solution. Okay, so we're gonna learn what molar solutions are today, and then this idea of dilution is a concept in this week's homework. And so what is dilution? It's when you're taking your solute and you're adding more solvent and you're just diluting it and making it less concentrated. And so we'll have some math associated with dilution. And so how is that related to pollution? I'll give you a great definition of pollution. It has 3 things. This is not on the test, okay, but it's on the test of life, right? We have pollution in our environment. So pollution has 3 parts to it. It's a concentrated substance that causes harm. So it's loss of control of a concentrated substance that causes harm. If you have control of it, it's not pollution. Okay? If it's not concentrated, it's not pollution. And if it doesn't cause harm, it's not pollution. So it has to have all 3 of those things. Okay? And so this middle piece, the concentration, that's what we mean by dilution. So you can take a pollutant and dilute it, and then it's not concentrated. And so it causes less harm or causes no harm. I mean, you have toxic things in your drinking water. You have arsenic in your drinking water. You got vanadium, but the toxin is the dose. And so if those are really dilute, then your body can handle it. It might kill 1 cell, but your body loses all kinds of cells, all the time. So you walk out in the sun and it's just killing cells in your skin, and you're processing those dead cells. So again, the toxin is the dose. And so if we could lower that dose by dilution, we'll learn the math of that today. Okay, I didn't dig up on the progress on tonight's thing, but I guarantee it's several of you haven't started it yet, so just a joke. Okay, so let's jump in. We're going to be calculating molarity and solute moles today, and we're going to use this molarity term many different ways. So we're going to go from moles to volume using molarity. We're going to do moles and volume to compute molarity. We're going to go backwards and forwards. Then we're going to add molar mass in there, and then we're going to work with dilution. Okay, this is all gearing up to that broader chemical reaction, the limiting reactant problem, and titration. But remember that top row is the lab units, and the middle 3 rows are chemical units where the chemical reaction takes place in moles. So we've got to be able to get from volume, like we measure a volume with a burette or we measure a volume with a graduated cylinder. That's a lab unit. And we got to get to moles, and that's what molarity gives us. So it's a way to get from chemistry units to lab units. So this is what we're dealing with solutions and concentrations. So remember your solubility rules in your cations and anions, right? Because you need to know what's soluble and what's not. But if you take something, a salt that is soluble, and you put it in water, it dissolves and it makes a homogeneous solution. And that salt is called the solute. And the whole mixture is the solution. So the solution is everything. It's the solute plus the solvent. The solvent is the thing that the solute dissolves in, but it makes a solution. Sometimes the volume of the solution is different than the volume of the solvent. So like if you take, let's say 100 mils of water and you put some salt in there, sometimes it shrinks. It's like 99 mils because the salt has pulled the water in closer. So the volume of the solution is a different thing than the volume of the solvent. So you take, X number of moles of some substance, you put it in a certain volume of solvent. That solvent, when it makes the solution, can change volume a little bit. So we always want to talk about volume of the solution, the overall volume. And this is going to lead to concentration. We could put more or less salt in the solution, and we could make a more concentrated or a less concentrated substance. So how much stuff is in a liter of solution? That's our concentration. And we're going to use this concentration value called molarity. There are other ways to talk about concentration. We could do, percent composition, like percent sodium chloride in the whole of the solution. We could do that by mass. So there's other ways to talk about concentrations, but today we're going to be focused on molarity. So what is molarity? Well, it's moles of solute, and this is the important word, liters of solution. It's not liters of water, it's liters of the whole solution, because that volume could change a slight amount when we dissolve it. And this is important because this is our conversion factor from lab units to chemical units. Because what are the chemical units? Well, those are the moles. And the lab units are liters. We measure with volumetric glassware. We have pipettes, burettes, beakers, graduated cylinders. We have lots of things with tick marks on them to measure volume. So that's something we can do in the lab very easily. And if we know the concentration, then we can use that concentration to convert from volume of solution to moles of solute. And now we're in the chemical units and we can do our limiting reactant problem and figure out what's going to run out and so on. So let's dive into the Alex problems. So this one says a chemist prepares a solution of barium chlorate by measuring 23.3 micromoles of barium chlorate into a 300 ml volumetric flask. And in the lab, have y'all seen volumetric flasks? Have y'all used those? No, okay. So let me just describe what's going on with the volumetric flask. So it's got this big bulb down here at the bottom to hold the large amount of fluid, but then this neck right here, notice if I add just a little bit more, this level of liquid's going to change a lot because it's in a real narrow part, right? So if I put a squirt of solution in there or water, it's going to rise up real quick. So it's real sensitive at this last part. So I fill it up with 300 mils. I get up here, it's real sensitive to just small amounts of liquid. So if I put a mark right here, right at 300 milliliters, then if I go, just one more drop more, it'll be too much volume. If I don't put enough in, it won't be quite 300. So we have these volumetric glass containers that are very accurate. Like it might even be, 300.0 mils, right? 4 significant figures because that neck is real sensitive to changes in volume. The problem with volumetric glassware, and we won't get into this in your labs, but the problem with volumetric glassware is temperature. Okay, because if I heat up that solution, if it's a hot day and the lab's AC is not working really well, then the volume's going to increase a little bit. Okay, and if it's a cold day, or if you're in my lab and it's like 17 degrees instead of 25 degrees for room temperature, it's going to be a really dense solution. The volume's going to shrink. And on the front of that glassware, it says 20 degrees C. Like almost all of this glassware is calibrated. So it's 300.0 milliliters at 20 degrees C. If you're off from that temperature, then you really should do a temperature correction. Now, that's not very easy. We would not ask you to do that at this level in your lab, okay? But you would look up the volumetric expansion of water, and if you're measuring it at a hot room and it's 27 degrees C, then you would fill it to the mark, but you would calculate the actual volume of that liquid at 20 C, and then you would be able to know what the accurate concentration would be at that temperature. Okay, but that's what they mean by this filling the flask to the mark with water, that phrase. So that's how we make our really accurate volumetric solutions. So we put it in a volumetric flask and very carefully with a pipette fill it up to that mark so we know it's 300.0 mils or 300 mils. Okay. Now this is asking to calculate the concentration in micromoles per liter of the chemist's barium chlorate solution. So this is pretty straightforward. We've got 23.3 micromoles of barium chlorate in 300 mils of water. And so all I need to do is just convert that over to micromoles per liter. So I can get out of milliliters and into liters. This right here should be as familiar to you as like the back of your hand. I'm going to draw a little hand right there. Okay. Getting from milliliters to liters, I mean, come on, there's 1,000 little milliliters in a big liter. Okay. So you should be able to go like that with milliliters to liters, milligrams to grams, all of those kinds of things. So milli is something, it's 10 to the minus 3. So here you have 10 to the 3 times 10 to the minus 3. Those cancel out. And So we're good. Okay, so this is in the correct units now because our milliliters have canceled. So the milliliters here is gone. So we take the 23.3 divided by 300 times 1,000. We have 77.7 micromoles of barium chlorate per liter of solution. Now that moles per liter of solution, this piece right here in red, that is molarity. And so we could also say that this is a 77.7 micromolar solution. Now, I don't know why Alex isn't using the capital M, right? It's in these problems that I did for today, this capital M here is the same as this moles per liter. It's confusing with mega. Is that what you're saying?
Maybe that's why they did.
It could be, but we've got to teach you the context. So the context, when M can equal molarity, and M can also equal mega. So how do we know the difference?
The mega would be in front of the molarity.
Yeah, so mega is in front of something. So all of those metric things, what are they called? They're metric prefixes. They're in front of something. So for M to equal mega, it would be something like megagrams. You see, it's a prefix. It's in front of G. So it would be capital M, G, that would be megagrams. Notice this M isn't in front of anything in terms of a unit. It's not in front of grams. It's not in front of seconds. It's not a prefix. It's just the M by itself. Now, it can have a prefix like micro. So this could be confusing if you're looking at it and you go micro mega. Micro mega what? Right? That's weird. But no, the micro is the prefix, and it's in front of molarity. So it's micromolar solution. If that confused the heck out of you, go back and watch the video slowly, like pause it, back up, so you understand what we're talking about. Okay, so going from moles to volume. So here we're going to use this. Calculate the volume in liters of this millimolar solution of copper fluoride that contains 2 moles of copper fluoride. All right, so here we've got a situation where we want to get to liters, okay, but we're starting with moles. And we're given the conversion factor. The conversion factor is the concentration of that solution. So we got 2 moles of copper fluoride, and we want to convert that over to liters. Now notice what I've done here. This is another way to convert out of milli something. So I can take that milli, and that milli is the same as 10 to the minus 3. So wherever you see that little m, you could just put in there 10 to the minus 3. If it was micro, you could put 10 to the minus 6. If it was nano, you could put 10 to the minus 9. You just take that little bitty letter out, that prefix out, and stick in the power of 10 that it represents. Yeah, thanks. There you go. Just there. Sure. So this works. Instead of writing M, I just put in 10 to the minus 3, and that cancels that milli. I could also put 1,000, millimoles per mole, and do it that way. This way works. This is a little shorter, and so what I would then do is 2 divided by 0.00218 times 10 to the minus 3, and then that's what I would get. Okay. So that's how many liters. I mean, again, I would need a lot of liters because it's not very concentrated. Not only is it millimole, it's 10 to the minus 3 moles, it's 0.00216. So it's like, we could rewrite that as 2.18 micromoles. Okay, this type of problem, different kind of problem in our module, where a chemist prepares a solution of sodium thiosulfate by measuring out a certain mass of sodium thiosulfate into a 50 mil volumetric. So you can see on your homework, I've got some little marks on what you begin with and what you end with. So let me emphasize on these problems. You always want to start with the end in mind, right? It's just like if you're a ship, you're going to find a compass point, and that's where you're going to head. So the compass point here is moles per liter. That's what the calculation is asking for, the red. So calculate the concentration in moles per liter. So this is where we're going to end up with a ratio. So if you're going to end with a ratio, you want to begin with a ratio. So what kind of ratio do we have in this problem? Well, we've got what we did. We took a certain mass and dissolved that into a volume. We have mass per volume, and we eventually want to get moles per volume. So we want to convert the milliliters over to liters, and that'll fix the denominator. And we want to convert mass over to moles, and that'll fix the numerator. So these are all just unit conversion problems. And in that larger problem of lab units, chemical units, that first, going from the first row to the second row, is all unit conversions. We could have a mass, and we're going to moles, so we need the molar mass. Or we could have a volume, we want to get to moles, so we need a molarity. And so these are the calculations that we would use to get out of the lab units and into the chemical units. So we need the molar mass for this sodium thiosulfate. So we have 2 sodiums, 2 sulfurs, and 3 oxygens. We get 158.2. And so we can put that in. We put it in upside down so that the grams cancel and give us moles. Okay, then what's next? Well, we get out of milliliters and go into liters. So 1,000 milliliters per liter. So we're out of milliliters. And now we've converted the numerator into moles. We've converted the denominator into liters. And so we've got our answer. So that's 3.9 moles per liter of the sodium thiosulfate. We could also say that's a 3.9 molar solution of sodium thiosulfate using the capital M instead of the moles per liter. Any questions on this one? Sort of raised it a little level.
Well, okay, never mind. So the 158.2 is, okay, that's the molar mass.
Yeah, I just used the table to add it all up. Yeah. And so that needs to also be as common practice. You know, it was a whole assignment earlier in Alex to calculate the molar mass. Now that has to be sort of in your toolbox so that you could do these. So it definitely builds. And chemistry does build on it. That's what makes a course pretty hard, because just because something was on the first exam doesn't mean you don't need it for the second exam. Because if you had to know how to calculate molar mass on the first exam, now you got to know that plus the molarity stuff. So it builds. Okay, now let's go from mass to volume. So we're given a particular mass of a substance, and we've got a concentration, and we want to know how much of that solution would deliver that amount of mass. Okay. So calculate the volume in liters of this molar solution of silver oxide that contains 6 milligrams of silver. So in this case, we're going to end with a single unit of liters. So we're going to begin with a single unit, the mass. Does that help? Because a lot of times when you look at these problems, you're like, what do I start? Where do I start? I've got all kinds of numbers, got chemical species. Always try to think, where do I want to end up? It's asking me for liters. Okay, that's a single unit. It's a liters. It's not moles per liter. It's just liters. And so I'm going to pick the other unit that is just a single unit. I've got a double unit up here. This concentration is millimoles per liter, and then I've got a milligrams. You see, this one is just a single unit, milligrams. So that's what I'm going to start with. So I've got 600 milligrams of silver oxide. I'm going to need the turn that into moles. And so silver is 107.9 and oxygen is 16. And so this is the molar mass, but I'm looking up there and I've got milligrams. And I'm also looking up here, my concentration is in millimoles. Okay, look at this trick. 123.9 grams per mole is the same as 123.9 milligrams per millimole. Does everybody agree with that? I've got a 10 to the minus 3 on top and a 10 to the minus 3 on bottom. There's no problem with doing that. And so now I can just write that upside down and my milligrams will cancel. This is totally legal. Okay. So I've got milligrams on bottom, and those cancel. I'm just trying to make the problem not so long, because you would have 1,000 milligrams per gram, and then you'd have upside down, you'd have 1,000 millimoles per mole, and all these different things, and you'd have all of these thousands on there, and they're going to just confuse you and cause you to make calculator mistakes. What if you get one of those thousands upside down? Then you're off by 6 orders of magnitude. So that can be a problem. And then we use the concentration, and the concentration is in millimoles per liter. So the millimoles is on bottom because I want to cancel with millimoles. So this is right out of the problem, the 7.9 times 10 to the minus 5. And this is the most efficient way to do this problem. Like I could do the 1,000 milligrams per gram and 1,000 millimoles per mole and so on. But those thousands would cancel. And so our answer then is 6.1 times 10 to the 4th liters. So we need quite a bit of it because it's not a very concentrated solution. So you just kind of do a gut check, right? I mean, I've got a really weak solution. It's 10 to the minus 5 millimoles. So really not a lot of copper oxide in that solution at all. And so if I need 600 milligrams, I'm going to need a large volume of it. Okay, so 10 to the 4th liters.
Can you explain one more time how your moles? It's just
This step here.
yeah.
Yeah, so I'm just looking at that. If I can do kind of like you have if you have an equation, you can do anything to both sides of the equation, right? Every equation can be written as a ratio, a conversion. And so you can do anything you want as long as you do it to both the top and the bottom. Yeah. So I could put anything. I could put a kilo in a kilo. Or I could any one of those prefixes I could put, as long as I put them on top and bottom, it's legit. Yeah. Yeah. Because if you were to just leave it like that, you would cancel them. Right? So I'm looking at this, I was like, well, I can cancel that milli and cancel that milli, and I have grams per mole. And me kind of going back. But I actually want to use this form in my problem so that I can cancel the milligrams in the beginning here. And then I end up with millimoles. We're really banging this drum hard on the millimoles because that's very frequently what the levels of concentration we have in the lab. And also because it's kind of hard for you guys. You're like, millimole? I know what a mole is, but what's a millimole? Well, it's 10 to the minus 3 moles. There's nothing spectacularly unique about that. And so we really want you to feel comfortable with millimoles and milligrams and milliliters. So everything that's on the lab scale of what we do with our hands. Now, if we're in industry and we're dealing with 300, gallon tanks and so on, then we're dealing with kilograms and kilomoles and stuff like that. But in your lab, we're dealing with milliliters and milligrams and millimoles. Okay, now this one has another twist. So now all of these get a little bit more complicated. So this chemist is preparing a solution of iron 3 chloride, measuring out a certain mass of iron chloride into a 100 ml volumetric flask, filling to the mark with distilled water. And now this is asking you to calculate the molarity of the chloride anions. So it's not asking you for the concentration of the whole thing. It's asking just for the chloride. Do you see that 3? It's Cl3. That's going to play a role. Okay. But first, what are we starting with? Where do we want to go? We want to go to moles per liter. Okay. So we're calculating the molarity in moles per liter of the chloride anions. And so then we begin with a ratio. So in our problem, we're looking at the problem. What kind of ratio can we make? Well, we have milligrams of chloride and 100 mils of volume. So we're going to put that as our ratio. So milligrams on top, milliliters on bottom. That's very similar to the moles per liter. We're going to convert the milligrams into moles, and then the denominator, the milliliters, into liters. And so that's what we need to do. To get out of grams and into moles, what do we need? Molar mass, right? So we got to calculate that. Iron's 55.8. 3 times the chloride gives us 106.2. So if we need to check that, just 35.4 times 3 is 106.2. So the molar mass is 162 grams per mole. Also, I'm looking over here at this problem, and I see milligrams and milliliters, And so I could just scratch that out and scratch that out as long as I cancel them with each other, right? So that would be the same as grams per liter. I could scratch out the milli and the milli. And so I'm working in grams, and I can go straight to grams per mole. And then this is the key here to the problem. This one right here. Where did that come from? It's right there in the formula, isn't it? So look at this. This is the 3 of iron 3 chloride. This 3 right here is this 3. When that dissolves, I get 3 moles of chloride ions for every mole of this stuff that dissolves. Now, I don't weigh out the chloride ions. I weigh out the iron 3 chloride as a unit. So I scrape that out of the bottle. I got 34.7 grams of the compound. But when it dissolves, then I've got triple the amount of chloride. And so that's typically, this is a very common calculation, because a lot of times maybe we want the reaction to take place and chloride is the reactant we're interested in. So we need to know the chloride concentration. We don't really care about the iron. Maybe the iron's going to be a spectator ion, so we're after the chloride. And so that's a 0.00642 moles of chloride ion per liter solution, or 0.00642 molar chloride. Can we write this in millimolar? But what do we do with the number? So remember, milli is small, right? By 1,000. And so this right here would be the milli place, right? So if we put the decimal place here, that would be millimolar. So that would be a 6.42 millimolar solution of chloride. And you can see why that's useful, right? Because again, we're dealing with small concentrations, and 6.42 is a lot easier to write than 0.00642 or 6.42 times 10 to the minus 3 molar. We don't have to have any times 10 to the minus 3. We can just move that decimal place and talk about a 6.4 millimolar solution of chloride. Any questions on this one? Yeah.
So if it's let's see if it's a whole equation or formula of iron chloride with oxygen, and then you balanced it out, and you had to put a 2 in front of the Fe chloride period.
Yeah.
Would that change the red section?
Yes. Yeah. So whatever, I'm trying to think of one that's more complicated than this. Let's do the calcium phosphate. Okay. So let me erase this guy right here so I have a little more space. So we take a 2 molar CaPO4. So what are my subscripts on this calcium phosphate? It's not this. I got to put a subscript by the calcium and a subscript by the phosphate. So phosphate's what? What are the charges on the phosphate anion, folks, in the back? 3 minus. Very good. So 3 minus, and the calcium, some other person in the back. 2. Very good. 2 plus. Okay, and so I got to get those to cancel out, and so then I get 3 calciums and 2 phosphates. Make sense? Okay, so this is a 2 molar solution of calcium phosphate. That may be what I weighed out. What is it in terms of phosphate only? So I would multiply that by 2. I don't have enough room to write moles, but I'll squeeze it in. Moles PO4 for every 1 mole of Ca3PO42. So this 2 right here, when that phosphate comes off, it gives us a 2 there. So this would be a 4 molar solution of PO4 3 minus. And then if the calcium, if I wanted to take that, I could multiply that number by 3 moles calcium 2 plus for every 1 mole of Ca2PO4, CO3, PO42, because of this 3 right here. All right, and so then that'd be 2 times 3, so that'd be equal to 6 molar calcium. But I can't weigh calcium out as ions. I can't go to the stock room and grab a bottle of calcium ions. I got to get what I get. And I might have the only source of calcium might be calcium phosphate. So I grab the calcium phosphate, I weigh that out. Okay. And then I convert that grams into moles of calcium phosphate. But I want to know how much calcium I have. So then I use this conversion to get out of calcium phosphate and into just calcium itself. So just using that formula, I get 3 moles of calcium ions for every mole of phosphate, and I get a mole of phosphate for every molar mass of grams of calcium phosphate that I weigh out of the jar. Okay. So this is a very, very common conversion factor, and it's kind of a mystery because it's not anywhere in the problem. It's in the formula. So that's why it can be tricky, right? You don't have like this one here you find on the periodic table. This one here you find in the formula itself, FeCl3. So there's more information in the problem than you just see. You're typically, when you're taking a test, you guys have been trained to do this, find the numbers, right? Well, there's more than just the numbers. Some of the numbers are on the periodic table. They're not in the problem. And some of the numbers are in the formula. Okay, so this is, we're just trying to teach you to be observant and to think through the problem. Okay, now we get into dilution. So I teach this 2 different ways. Does anybody know the equation for dilution without looking at the notes? Did you know this before you got here? Anyone? A few people? It's that M1V1 equals M2V2. That's the dilution equation. But you can teach it 2 different ways. And so this is the first way, using the subscript method. And I think this is a different, I mean, I like this method because it keeps me from making mistakes. I think it's pretty straightforward. So what have we got? Well, we're going to moles per liter. We're ending with a ratio. And so we're going to begin with a ratio. And so we're looking up here at the top. We're looking at this concentration of the stock solution, right? So this milliliters is not a ratio. This milliliters is not a ratio, but this one is moles per liter of stock solution. Okay, but I've got to keep track of the 2 solutions. I've got a stock solution and I've got a working solution. What are we talking about? Stock and working. Can anybody tell me what that means?
Get from stock or like.
That's a good way to think of it, yeah.
And then the working is what you need for the solution.
Mm-hmm. So a lot of times we make a stock solution that's really concentrated, okay? But we don't want to work with such concentrated materials because, one, they can be more dangerous, like they can harm your skin and so on if it's really concentrated. And so for the lab you're actually going to do, we want to dilute it to a working solution. So I can make up a jar of sodium hydroxide for you guys to use in titrations. I can make up in one jar all the sodium hydroxide that all 70 of you guys need if you'll dilute it. So you take a small amount, you add water, and now you've got a dilute solution that you can use, and a dilute solution you can use, and so on. But I only have to make up one stock solution. So stock solutions are typically way more concentrated than the working solution. The working solution is what you're working with at the lab bench. Stock solution is your source. So you can take your bottle and weigh out a whole bunch of solute, dissolve it in water, and make a really concentrated stock solution. And then you can take a certain amount of liquid out of the stock solution, add more liquid, and make a dilute working solution. So that's what we're talking about here. So I'm just going to use subscripts on all my volumes to keep track of these things. So here I have a liter of this concentrated iron bromide in a liter of stock solution. And then I'm going to use the other 2, but I'm going to put subscripts on them. So look at the 60 mils Okay, I've got 60 mils of the stock solution here, right here. And how do I know that that should have this subscript stock on it? Well, look up the problem. It's 60 mils of the stock solution right there in the text. So I'm going to put stock as a subscript on that volume. And then I want 90 mils of the working solution. So it says right here, 90 mils of the working solution. Okay, so that's going to have this subscript working. So this is totally legal too. You can put subscripts on anything you want to help you keep track of things, because it's volume and volume. Well, liters is liters, right? But there are different kinds of liters. There's liters of the stock solution. There's liters of the working solution. So you can add subscripts if it helps you keep track of the problem. And so we look at this, we see the millis cancel and all of that stuff. And so it's very simple. 3.87 times 60 divided by 90. We get 2.58 moles per liter of the iron bromide, or 2.58 molar iron bromide, iron 2 bromide. So pretty straightforward using the subscripts. I don't know if anybody else teaches it this way, but I think it's very, very useful. Okay, let's do it the different way. This is the way the book teaches it, and maybe even Alex, and using this dilution equation. So here I've color-coded it for you. So we've got 3 different colors here, and here's our equation that's color-coded for you. So M1V1, M is representing molarity or concentration. Sometimes they say C1V1 equals C2V2. So you can see this 2 different ways. I use M because it reminds me of molarity. So the molarity of solution 1 times that volume equals the molarity of solution 2 times that volume. And so this is the dilution equation, something you could cram into your head. And so all we need to do is solve for the concentration. When we're looking at this is calculate the concentration of the working solution. So that'll be M2. So we just solve for M2. M2 is equal to M1 times the ratio of the volumes. And so then we got to go to the problem and see what the V1 and the V2 and the M1 are. Okay. And so the orange and the blue, that's M1 and V1, and then the red is the V2. So we can put those numbers in. The only downside of using this equation is sometimes you can get this upside down. Okay, if you get that upside down, you will not be able to know, because the units all cancel and everything looks beautiful. But the thing is, you would have to look to see if the concentration got smaller. If you're diluting it, if you're going from 60 mils to 90 mils, you've got a larger volume, so the concentration should go down. If you get those volumes switched, the concentration will go up, and that doesn't match with what the problem is saying. So you would be making a working solution that's more concentrated than your stock solution. But that requires thinking. You got to look at the output of the problem and go, yeah, this doesn't make sense. I got my volumes wrong. Okay. So this is, again, the same answer we got before. It was the same calculation, but just different method. So 2.58 moles per liter of the iron bromide. So that's one of the Alex problems on dilution. What I want to do now is I want to give you another one of these problems, but instead of solving for the concentration, I want to solve for a volume. So we're going to have 2 concentrations and then a volume that you have to solve for. So let's do that. This is dilution using the subscript method. So this is the problem that I made up. I don't know if Alex gives you any of these. So I want 500 mils of a 0.1 molar working solution. How many mils of this really concentrated stock solution do I have? So this is an example of what you would actually do in the lab. You have a 10 molar sodium hydroxide solution, really dangerous to work with, 10 molar. That'll eat your skin. I mean, it'll hurt you. But a 0.1 molar sodium hydroxide solution, not so concentrated. If you get a little splash of that on your hand, you can wash it off, and it's not concentrated enough to damage your hand before you can wash it off. If you leave it on your hand, yeah, it could still damage your hand, but it's better to work with dilute solutions. So how many mils of the stock solution do I need to put in my 500 mil flask? is the question. So again, where are we beginning, or where are we going towards? We're going to end with the volume, so we need to begin with the volume. So we're going to begin with that 500 mils, and we're going to put a subscript on it. So that's my working solution. And then I've got a couple of concentrations here. So I can, again, put subscripts on anything I want. So that working solution, I want to cancel the volume of that working solution. And so I need my concentration of the working solution to be written like this. And I want to get into the volume of the stock solution. So I need to write that stock solution like this. So you see the subscripts are on the volumes. And now I'm canceling the volume of the working solution, and I'm getting a volume of the stock solution. So and you can look at to see how these things cancel. So the moles cancels with moles, and then the working cancels the working. You can think of it that way. And the liters actually cancel the liters, and I'm left with milliliters and the subscript stock. Okay, so you can, it all works out. Okay, and so I end up with 5 mils of the stock solution is what I need. So that's pretty easy to do. I can do that with a single pipette, really. I can pipette 5 mils out of this really concentrated stock solution. That's the most dangerous operation in the lab then, is getting that 5 mils out of this concentrated bottle, putting it in a 500 mil beaker or volumetric flask. We can do the same thing with the dilution equation. Here's my 3 color-coded things. I've got a concentration, M1 in orange. The volume of that is 500 mils. That's my working solution on the left. On the right is my stock solution. I've got the concentration of the stock solution, but I don't know the volume of the stock solution. So I would solve for that volume 2. It's volume 1 times the ratio of the concentrations. And so I want 500 mils of the 0.1 solution, and I divide by the stock solution concentration. And I end up with 500 mils, or 5 mils. So I take 5 mils, put it in the beaker, and add in the solution. Oh, let me tell you this too. So whenever we've got base here, but it also works with acid. So if we had a really concentrated acid and I want to dilute it, do you know that there's a sequence to how you do that? Acid to water. You add acid to water, not water to acid. Okay. And so how do you remember that? I like try to do my best Boston accent. Okay. So you know how to Boston people, they don't pronounce the R's, right? Pak to kaba to cab, right? So you do as you oughta, add acid to water. That's how you're supposed to do it. Do as you oughta, add acid to water. Okay.
It's also alphabetical.
Oh, that's nice too.
Like A.
Yeah.
Go for W in the alphabet.
Oh, that's good. I like that. Okay, so we've got 6 minutes. So let's do a Kahoot. You ever guys do a Kahoot?
So, but the M1 and
Yeah.
V1, the M1's always going to be your working.
It's however you want to do it. It doesn't have to
I
be.
guess 'cause, yeah, it's equal.
Yeah, 1s and 2s. But you got to decide what volume goes with what concentration. So you find 3 out of the 4 and solve for the 4. Yeah, and whether it's a 1 or 2 doesn't matter.
Whatever you decide is going to be 1.
Yeah.
All of it but a B.
All right, so this is a pretty quick Kahoot. I can't believe I closed that down. Let's go right here. Okay, and go to kahoot.it if you want. I'll get you the game code here. Where's my library?
I did.
All right, here it comes.
You laugh. Waiting for all the stickers.
That's right. Is it coming up? Okay, we got to start it. Got that rocking music. I'll get it going in a second. I love the sound, yes. All right, so
I have no idea what this is.
You know?
Oh, I guess. Okay, so go to Kahoot.it.
Yeah.
And then you're gonna put in the game pin. And then you put in.
No. No.
Okay, yeah.
I'm 35 years old.
It's
Questions?
yeah.